away from the axis, right, that increases the moment of inertia. Next, we look at angular momentum. You guys already know what momentum is, but now angular, when something rotates, it's got angular momentum. Now, there's actually a lot of cool demos with angular momentum, which we'll show you guys in the next few days here. But angular momentum is actually labeled with the letter L, okay, and it's measured in kilogram meters squared per second. Kilogram meters squared per second. So it's really your mass times your momentum vector. So you go ahead and have those units. Now, again, the equivalent, you probably guessed, is momentum, linear momentum with lowercase p. Here's a couple equations for us. You guys already know what the other variables mean. I, moment of inertia. We got omega, the Greek letter omega, which is the angular velocity, right? So that's essentially your mass times your velocity if we think about it in terms of linear motion. So it should make sense there. All these equations are on your equation sheet, so there are no surprises at all. Finally, we have rotational kinetic energy. Now, this one's interesting, and I want you guys to think for a second about this. If you think back to the energy unit, Unit 4, when we talked about energy and we did conservation of energy and things rolling down a hill or something along those lines, if you guys remember, all those problems that we did all had masses that were pretty much sliding, whether it's a box or a sled or whatever it was always sliding. We never had anything rolling, and that's for a reason. Because when something rolls, like a ball or maybe a cylinder, like we did a demo of the other day in class, right? There's rotational now kinetic energy. So that doesn't mean that all of a sudden 1/2 mv squared doesn't exist. It absolutely does. 1/2 mv squared is actually translational kinetic energy. Translational just means from side to side, right? So when something slides, it's got translational kinetic energy. This is your 1/2 mv squared equation. But the equation for rotational kinetic energy is actually 1/2 I omega squared. Very similar equation, but we have to take that into account. So yes, that means that a ball that is rolling, if it's rolling at the same speed as a box, let's say, with the same mass that's sliding with the same velocity, if they're moving together, the rolling object does have more kinetic energy because it's got translational kinetic energy, 1/2 mv squared, just like the box, but that ball also has rotational kinetic energy, so you would add those two. And in the coming days, if you look ahead in the notes, we will do at least one example like that so you guys can see that conservation of energy law with rotation, but it's no different. Just understand that rotational objects, things that rotate, do have a kinetic energy as well, and here's the equation for it. So to wrap up these video notes, I want to show you guys a couple additional equations that are good to know. Now, these are not on your equation sheet, but I like these because they sort of relate rotational motion with linear motion. So, you know, for example, as I was mentioning earlier, if you have something spinning, right, depending on how far that mass is from, or that object is from the center, something that's further out is going to have a greater tangential velocity than something that's close by. But I mentioned that the angular velocity, omega, is the same because it covers the same amount of radians, you know, in the same amount of time, however many seconds. So really that relationship there for omega, the angular velocity, is just your tangential velocity divided by your radius. Similarly, for alpha, for angular acceleration, the relationship there is acceleration, tangential acceleration, divided by the radius. So again, both equations allow us to kind of connect the two together. Now I do want to point this out, last thing here. So for the note, right, so we've talked about already in the past centripetal acceleration. Centripetal acceleration is not the same thing as angular acceleration. If you remember, centripetal acceleration equals v squared over r, right? We usually use that with objects that spin in a circle, right? If there's a centripetal force on something, then there's a centripetal acceleration on it. It doesn't actually have to be speeding up at all. Its velocity, the magnitude of the velocity does not change. However, with angular acceleration, Angular acceleration literally means that the angular velocity increases. So like the example that we did last unit with twirling a ball on a string in a circle, whether it was the demo in class or the lab we did or whatever, that had a centripetal acceleration because the velocity was always changing direction, but it was still moving at a constant speed. Angular acceleration means that it literally is picking up speed as well. It's increasing its velocity, its angular velocity. So there is a big difference between the two, so just something to keep in mind. Thank you for taking good notes, and we're going to continue doing a couple of the examples on the next few pages.